Welcome to this presentation in the series Electronics, the Story of One Human Lifetime, presented by David Beams and Gary James. I am David Beams, Associate Professor Emeritus with the University of Texas at Tyler. And today's video concerns a mind-bending problem from the distant past. In 1972, I was entering my junior year in electrical engineering at the University of Illinois. I was taking Electrical Engineering 262, Linear Circuits Analysis 2. It was a required course. Now, this was the course in which the Laplace Transform was introduced. And the Laplace Transform, of course, is a foundational concept in the practice of electrical engineering. The professor teaching the course was known for his mind-bending exams with trick questions. The exams always had a total of 30 points. Why 30? No one knew. On that first exam that semester, I scored 13, and that was enough to earn me an A. Okay, let me show you the first question on the very first exam. I remember this question to this day. You have two parallel LR branches connected to a voltage source, and they're connected through a switch. And this switch has been closed since the time of the pharaohs. So the currents in each branch have reached their steady state values. 3 amps in L1, 1 amp in L2. But at time t equals 0, some darn fool who should have known better opens the switch. And we were asked to find an expression for the circulating current for t greater than or equal to 0. We'll first go through a rigorous solution using the Laplace transform, and then I'll show you what I did on the test where I tried a quick intuitive solution. This is the network drawn for Laplace transform analysis at t equals 0 plus. The initial conditions are represented as step current sources in parallel with initially unenergized inductors. We'll apply Kirchhoff's voltage law and Kirchhoff's current law to this network. Kirchhoff's current law tells us that the sum of the current in L1 plus the initial current step source plus the current in L2 plus the initial current step source must equal 0. And Kirchhoff's voltage law tells us that the voltage across L1 plus the voltage across R1 minus the voltage across L2 minus the voltage across R2 must sum to 0. And we have supporting relationships that in the Laplace domain, the voltage across L1 is SL1 times the current in L1. The voltage across L2 is SL2 times the current in L2. And the circulating current is just the current in L1 plus its initial current source minus the current in L2 minus L2's initial current source. Now, I'll omit the algebra because you can do that yourselves. You don't need my help to do that. And if you do that, you get this expression for the circulating current. And if we apply the inverse Laplace transform to go back to the time domain, we get a first order exponential decay. We kind of expect that. And with some initial value of current, and the initial value of current is given by this expression. And with the component values that were in the circuit, the circulating current that we compute from this analysis is 2e to the minus t. So let's verify our answer. Let's simulate this circuit with LT Spice and see how simulation results compare to our manual analysis. This is the LT Spice circuit. And in the analysis, this is a circuit for transient analysis with pulsatile current sources. Pulses that switch on go to 3 amperes at t equals 0. This one goes to 1 ampere at t equals 0. Let's see how the circulating current is calculated by LT Spice. And we get just what we expected. An initial value of 2 amps. You see it drops to 37% of its initial value after 1 second, which gives us a time constant of 1 second, which we're expecting. So this is exactly what we expected to see happen. So far, so good. But now I didn't have time during the test to do this kind of a detailed analysis, and I'm not sure thinking back that we had even seen the Laplace transform yet. So how did I try to work the problem? Well, I realized that after the switch opened, the test problem was just a series RL circuit that had an initial value of current. And the time constant was easy to compute because you just add the inductances to get the total inductance and add the resistances to get the total resistance. The fact that there were no mutual inductances made the problem much easier. So I knew that the solution would take the form of some initial value of current times e to the minus t. So far, so good. However, how do you find the initial value of the circulating current? I thought, I don't know. Maybe I can use energy conservation. Let's try that. So I added the energy stored in L1 just before the switch opened, and the energy stored in L2 just before the switch opened, and set them equal to the energy present in L1 and L2 immediately after the switch opened. In solving this equation, I got a value of I0 of 2.646 amps. And it turned out I was wrong. And LT Spice says I was wrong. But I really, at that time, I wouldn't have known why. Well, when the graded exams were returned, the professor asked, "Are there any questions?" And hands went up all over the classroom. And the professor called on one student who asked him, "How do you find the initial current in problem 1? And the professor said with obvious surprise, "Well, you use the method of constant flux linkages." And the entire class, with the exception of one guy who had gotten the right answer somehow, said, "The what?" "The method of constant flux linkages. You learned that in EE 260. That was our first circuit analysis course at the University of Illinois. And we all turned to each other and asked with great puzzlement, "Have you ever heard of the method of constant flux linkages?" And no one had. So what is this method of constant flux linkages? Well, let's start with the definition of inductance, which is flux linkages per unit of current. Now, the unit of inductance, by the way, is the Henry. 1 Henry is 1 volt second per ampere. So the unit of flux linkages is the volt second. Anyway, just before the switch opens, the flux linkages in L1, which I'll call here as lambda 1 or L1 times the value of current in L1 just before the switch opens. Immediately after the switch opens, the flux linkages in L1 are L1 times the initial value of the circulating current. So the change in the flux linkages is L1 times the difference between the initial value of the circulating current plus the initial current just before the switch opened. But now let's take a look at L2. Look at the distinction here between L1 and L2. You notice that the current in L2 has reverse directions. So the change in flux linkages in L2 is L2 times IO, the initial value of the circulating current, plus IL2O, that is the initial value of current before this in L2 before the switch opened. Constant flux linkages require that these sum to 0. And so if we write out the condition for constant flux linkages, we get this relationship. And from this, we calculate the initial value of the circulating current. And if we realize that IL10, that is the initial value of current prior to opening the switch, is the initial current in L1 prior to opening the switch is VB divided by R1, and the initial value of current in L2 prior to opening the switch is VB divided by R2. This expression for the initial value of the circulating current is the same as the one that we got from the Laplace transform analysis. Why didn't conservation of energy work for me, though? Was energy conservation somehow violated? Well, one thing I will note here. The previous circuit that we used for the Laplace transform analysis is valid for t greater than or equal to 0 plus. It does not represent the circuit for times prior to t equals 0. So we can't look at the behavior of the circuit across the transition with the Laplace analysis. So let's consider a SPICE circuit. And here, the voltage source and switch of the original problem are replaced by a pulsed current source. The initial value of the current is 4 amps. It's divided 3 amperes in branch 1 and 1 ampere in branch 2. The current source drops from 4 amps to 0 amperes at t equals 1 second. By putting the transition at 1 second rather than 0, we can look at the behavior of the circuit across the transition. And this pulsed current source has a fall time of 10 microseconds since SPICE does not allow instantaneous changes in voltages and currents. Voltages and currents that have pulsatile waveforms always have associated rise and fall times. And here are the results for the currents in the two inductors. The first trace here you see is L1. It's 3 amps at t equals 0 minus, and it drops to 2 amps at t equals 0 plus, which is what conservation of flux linkages told us would happen. The energy that was stored in L1 was 13.5 joules at t equals 0 minus, and it drops to 6 joules at t equals 0 plus. The current in L2 goes from 1 amp at t equals 0 minus to minus 2 amperes, a total change of 3 amperes at t equals 0 plus, and the energy stored in L2 goes from 0.5 joule to 2 joules. So the energy stored in the inductors just before the switch opened was 14 joules, and it dropped to 8 joules immediately after opening the switch. Where did the 6 joules go? Now here's a plot of the power dissipation of the current source I1 prior to t equals 0. The power dissipation was minus 12 watts, meaning it was delivering 12 watts to the circuit. However, just as the switch opens at t equals 0 plus, the power dissipation jumps to 1.2 megawatts and drops linearly to 0 at 10 microseconds. The total energy dissipated in this pulse, integrating the area under this curve, is 6 joules. The source absorbs the missing energy. So why is there such a huge power spike? Well, here's a plot of the voltage across the current source in the interval of transition. The huge voltage spike is due to very large values of di dt in the inductors. If you built the professor's circuit, opening the switch would produce an arc that would help dissipate the extra energy. I used to tell folks that the arc would blow the switch off the wall. It's probably not that much energy, but it would still be an impressive arc nonetheless. So energy is conserved, and so are the flux linkages. And the world goes on as it always has. Now, so a couple of human interest stories that go along with this presentation. In that particular class, we had several people who contributed to a kitty, pot of money, on a day when the professor was passing back an exam. We started doing this after the first exam. And the practice was that the person in the pool who got the lowest score would win the kitty. Across the street from the electrical engineering building was a bar that was called Wits End. Now, the kitty was not a lot of money. You couldn't use it to drown your sorrows, but you could use it to make them tread water for a while. And there was a guy in the class whose name was Dennis. Dennis was short, a little on the heavy side, and bearded. So, of course, his nickname was Bear. And Bear was one of the guys who contributed to the kitty. And I remember poor Bear, he won the kitty twice in a row. And there's another story that goes with this presentation. I had a roommate at the time who was an architecture student whose name was Mike. And in the class with me was a guy named Don. And they both sang in the same church choir on campus. Now, I knew both Mike and Don, but Mike and Don didn't know that they both knew me. So one evening after choir practice, Don is talking to Mike, and he is telling Mike about this tyrannical professor who gives these incredibly difficult problems on his exams. Just, oh, guy's terrible. And just laying it on thick. And Mike says to him, yeah, my roommate has a guy who's just like that. His name is, and he gives the professor's name, and Don spits out his coffee and doubles over with laughter and says, that's the that's the male offspring of a canine mother that I was talking about. Anyway, thank you for watching. Look forward to the next one in the series.